Hi everybody, so in this video we're going to be talking about Chapter 1. We'll continue with Chapter 1, which is Number and Algebra Basics. Specifically, we're going to be talking about scientific notation, also known as standard notation. So we're going to go through the different ways in which we write numbers in this notation.
So next is example 1.19, write in scientific notation.
So for example A, we have the number 35. So 35 you would write in scientific notation as 3.5 times 10 to the 1. So notice that basically what we have to do is use one digit, only one digit before the decimal point, and that digit has to be a non-zero digit that is less than or equal to 9. So that means that you can go from 2, 3, 4, 5, 6, 7, 8, or 9 in this first position. And then you have the decimal point and whatever other digits after that. And then you times it, a power of 10, that would give you the original number. So notice that if you multiply 3.5 times 10, you're going to get 35 because you only have to move the decimal point one position to get 35. So B is similar because we have 146, and that would be the same as 1.46 times 10 to the 2. For C, we have the number 65,000. So 65,000 would be 6.5 times 10 to the power of 1, 2, 3, 4 times 10 to the 4. D is a little bit different because D has a decimal point, so it's the number 78.65. So the rule is, again, one digit other than 0, so that would be 7, then the decimal point, so 7.865 times 10 to the 1 because we only needed to move one place. E is the number 300 million. So let's write 300 million. And this would be 3 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8. So now we're in example 1.20, and they ask us to write in scientific notation these numbers. So the first one is 0.1. So these are numbers that are less than 1. So notice that 0.1 is the same as saying 1 divided by 10. Or you can also say that this is 1 times 1 over 10. And recall from the rules of exponents that this is the same as saying 1 times 10 to the minus 1. So the negative exponent in scientific notations, really what it represents is division, or moving the decimal point to the left. So what we're saying here is 1, and then move one decimal point to the left, which would give us 0.1. So how do we write a number like B? 0.045. It's very simple. Remember that the rule is first a digit that is non-zero, followed by the decimal point, and whatever digits come after that. So 4.5, and in this case, times 10 to the power of negative 2. So it's always going to be these zeros to the left of that digit, which will be our first digit. So notice that we have two zeros. If it's 4.5, this means move the decimal place 2 places to the left. Notice that that would work perfectly. This would be 1 place and then 2 places. But it's much easier just to use the zeros to the left as a reference. So for C, where we have 0.00607, we can write this in scientific notation as 6.07 times 10 to the negative 3. Notice that it's 1, 2, 3, negative 3. So next we will do example 1.21. Part A says, Albert Einstein's famous equation, E equals mc squared, relates energy in joules, mass in kilograms, and the speed of light, c, which is equal to 3.0 times 10 to the 8 meters per second. Then it says, calculate the energy of a proton, and the mass of a proton is 1.67 times 10 to the power of negative 27 kilograms. So what would be the energy of a proton? Basically, all we have to do is substitute in this formula. So energy of a proton is going to equal its mass. So in this case, it's 1.67 times 10 to the minus 27 kilograms, but I won't write the units here. So notice that this is a very, very small number. This negative 27 indicates that we have 27 zeros to the left of the 1. Then we have to multiply this by c squared, and c is a fixed number. The speed of light in a vacuum is 3.0 times 10 to the 8 meters per second. We won't write the units until the end for the answer. The units for the energy are joules, so the answer will be in joules. Okay, so how do we, oh, this squared, I forgot, this squared. So how do we do this? Well, from order of operations, we would have to do this first because it's to the power of 2. So let's rewrite this as 1.67 times 10 to the minus 27, and this times this number squared. So here we use this rule. Remember that if you have a, b to the power of, say, n, this is the same as a to the n times b to the n. So this would be 3.0 squared, and 3.0 squared is going to be 9.0. So 9.0 times 10 to the 2 times 8, so times 10 to the 16. So here we have the multiplication of these two numbers in standard or scientific notation. We can treat this just like we would treat powers. We can multiply the 9 times a 1.67. So we're going to do that using the calculator. So now we're going to multiply 1.67 times 9.0. And that gives us 15.03. So we get 15.03 times 10 to the power. And notice that here we have exponent 16 and exponent minus 27. Now the deal here is that because it's a multiplication, we should add the exponents. So we're going to add negative 27 plus 16, which would give us negative 11. But this is not the right answer yet, because notice that we have 15.03, and scientific notation says that we have to have only one digit before the decimal point, and the digit has to be greater than 0. So we would have to write this differently. But notice that we can write this number in scientific notation, because 15.03 is the same as 1.503 times 10 to the 1. So this times 10 to the minus 11. And then we can add this exponent with this exponent, and we end up with 1.503 times 10 to the power of negative 10 joules. So the energy of a proton will be equal to 1.503 times 10 to the negative 10 joules. So now we go to part B, and it says the time t in seconds that it takes for light to travel a distance d in kilometers is given by the formula
T equals D over C, where C is the speed of light, 3 times 10 to the power of 5 kilometers per second. The distance between the sun and the earth is 1.5 times 10 to the power of 8 kilometers. Calculate the time t taken for light from the sun to reach the earth. 1 in standard form and 2 to the nearest minute. So for 1, we would apply the formula that time in seconds is equal to distance in kilometers over the speed of light in kilometers per second. So then the distance from the sun to the earth is 1.5 times 10 to the 8. And this divided by the speed of light in kilometers per second. So this would be 3.0 times 10 to the 5. So here we apply the rules for division. So we have to divide, first of all, 1.5 by 3.0. So let's use the calculator. So 1.5, well, not 15, it's 1.5 divided by 3.0. And that's going to equal 0.5. So this will equal 0.5 times 10. And here we have to decide on the power of 10 because it's going to be 8 minus 5 times 10 to the power of 3 seconds. But this is not the correct standard form or scientific notation. So notice that we can rewrite 0.5 as 5 times 10 to the minus 1. And then we have to multiply it by this, so times 10 to the 3 seconds, which is the same as 5 times 10 to the 2 seconds. So now for part 2, they want us to calculate this to the nearest minute. Now 5 times 10 to the 2 seconds is the same as 500 seconds. So how many seconds are there in 1 minute? We can convert this because 1 minute has 60 seconds. So this will allow us to cancel out the seconds and get the answer in minutes. And it's going to be 500 divided by 60. So notice that we can cancel out a 0 here. 50 divided by 6. The closest minute to this will be 8. So this is approximately, notice that we don't use the straight equal sign, but these curvy equal signs, which mean approximately 8 minutes. And last but not least, we have part C. So it says the population of the German cities Munich and Frankfurt in 2017 were 1.43 times 10 to the 6 and 7.76 times 10 to the 5, respectively. How many more people live in Munich than in Frankfurt? So this requires a subtraction. So we would have to subtract from 1.43 times 10 to the 6, we would have to subtract 7.76 times 10 to the 5. Now this is a subtraction that we cannot do using scientific notation, at least not with different exponents. We would have to have the same exponent. So there's several ways to do this. One way to do it would be to convert this into a normal number, right? Just moving the decimal point 6 times in the 1.43. So if we did that, we would get 143. So that's 2 decimal points, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So that means 1,430,000. And then 7.76, this could be written as 776, so that's 1, 2, and we need 3 more. 1, 2, 3. Notice that we have now 5, right? After 7, 1, 2, 3, 4, 5. So 776,000. So in the calculator, we write 1,430,000 minus 776,000, and that equals 654,000. So this equals 654,000. But we need to write this in scientific notation again. So this is going to be 6.54 times 10 to the power of 5. So the other way of doing this is more useful when we have numbers that are even larger, and it would be difficult to convert them to normal notation and then doing the operation and coming back to scientific notation. So how would you do it? So if you have 1.43 times 10 to the 6 minus 7.76 times 10 to the 5, in order to be able to subtract, we would have to have the same exponent for base 10. So we picked the highest one, and this is the highest one. So we need to move this to having an exponent 5. So how do we move this to have exponent 5? So notice that this means move the decimal point 6 places to the right. So if I move it 1 place to the right, I would have left still 5 places to move it to the right. So if I could write this as 14.3 times 10 to the 5 minus 7.76 times 10 to the 5. So now that both these numbers are to the same power, I can subtract their coefficients. So I would simply have to go 14.3 minus 7.76, and that's just going to be 6.54. And then we rewrite times 10 to the 5.